So what are we going to discuss today? We're going to discuss solution of Laplace equation in general cylindrical coordinates. So solution of Laplace equation in general cylindrical coordinates. Okay, solution of Laplace equation in general cylindrical coordinates. Okay, the Laplace equation is Laplacian of u is equal to 0. Okay, Laplacian of u is equal to 0. And in cylindrical coordinates, let me write it. Rho phi z. In cylindrical coordinates, the Laplace equation is in cylindrical coordinates, the Laplace equation is 1 by rho dy d rho dou u by dou rho plus 1 by rho square du by square plus du by dou z square. This is equal to 0. We call it equation number 1. This is Laplace equation in cylindrical coordinates rho, phi, and z. From this, we know that from this equation, we know that our u is a function of r, theta, and z. So in this equation, u is a function of rho, phi, and z. Therefore, by the method of separation of variables, u may be written as u is a function of rho, phi, z. This may be written as this. We can write it as capital R, which is a function of rho, then capital phi, which is a function of small phi, and capital Z, which is a function of small z. Okay, this we call equation number 2. Here capital R is a function of only rho, capital phi is a function of the angle phi only, and z is a function of small z only. Okay, so substituting this value, let me make it space. Okay. Substituting the value of u in equation 1, we get, now let us substitute this in equation number 1. We get 1 by rho, dou by dou rho, dou by dou rho of r phi z plus 1 by rho square, the second order partial derivative of r phi z with respect to phi square, plus the second order partial derivative of r phi z. This is equal to 0. See, here only r is a function of rho, phi and z are not functions of rho, so I can take phi and z outside. So this implies phi z by rho by dou rho. Okay, sorry. This dou by dou rho, it can be replaced by d by d rho now. D by d rho. Rho dr by d rho. Plus, now this r and z, they are not functions of phi. So I can take r and z outside. R z divided by rho square. So this is the second order derivative of capital phi with respect to the angle small phi square. Plus, here r and phi are not functions of z, so r and z can be taken out. Sorry, r and phi, r and capital phi can be taken outside. So this is d2z by d small z square. This is equal to 0. Okay. Now we divide both sides. Dividing both sides by r phi z, we get, so we divide both this left hand side as well as the right hand side by r phi and z, and what do we get? We get 1 by rho times r, d by d rho dr by d rho, plus 1 by here we get rho square capital phi, d2 phi by d phi square, plus this we get 1 by z, d2 capital Z by dz square. This is equal to 0. Okay, then we can simplify this equation. Let me write it on a new sheet of paper. What do we do? What do we do next? Next, what we do is we keep 1 by z dz by this 1 by z d2z by dz square on the left hand side, and we take these two expressions towards the right. Okay, so this implies 1 by z d2z by dz square. Okay, this is equal to minus 1 by rho times r d by d rho times dr by d rho minus 1 by rho square phi d2 phi by d angle phi square. Okay, this we call equation number 3. Okay, so this is equation number 3. Now in equation number 3, the left hand side is a function of z only, while the right hand side is a function of rho and small phi. Okay, so in this equation left hand side is a function of z, only z, while the right hand side is a function of rho and phi. Therefore, rho and phi only. Therefore, each side must be equal to the same constant, Let us call the constant k square. See, that is 1 by z d2z by dz square. This is equal to k square. This implies d2 capital Z by dz square minus k square capital Z. This is equal to 0. This is equation number 4. And this right hand side, we should get minus 1 by rho times r d by d rho times dr by d rho minus 1 by rho square capital phi d2 capital phi by d small phi square. Okay, this is equal to k square. Okay, this is equation number 5. Now you see this term contains only rho and functions of rho, that is r, whereas this term contains functions of phi, and we also have rho square here. So if I multiply throughout by rho square, this rho square will get cancelled out, and then this term will depend only upon phi. So let us do that. Multiplying equation 5 by rho square, we get this will be, see, rho square by rho, so this will be so say the rho by r d by d rho dr by d rho. Okay, here we have the minus sign here, and the GMO here minus this rho square, so this will be 1 by phi d2 phi by d phi square. Okay, and this is equal to k square r square. Okay, this is fine. Okay, now let us open this bracket. Okay, so this is minus rho by r. So let us open this bracket, minus rho by r. So d rho by d rho, that is 1. Yes.
See, small r square already combined.
Oh, sorry. This is not r. Sorry. This is rho. Sorry. Thank you. This is not r square. This is rho. Okay, Yareka.
Oh, yes.
Rho by r. This is d by d rho. So d rho by d rho. This is 1. So this is dr by d rho plus Rho you keep this row, then we differentiate this with respect to rho. So this is rho square. Okay. So see, when a product will palaga expand minus 1 by phi d2 capital phi by d phi square. This is equal to a square rho square. Okay, this is fine. Now I multiply by rho and rho by r. So I should get rho square by r. So minus 1 multiplied throughout the so rho square by r d2 r by d rho square. Okay, rho square by r d2 rho by rho square plus rho by r dr by d rho. Now, plus 1 by phi d2 phi by d small phi square. This is equal to, I have multiplied throughout by minus 1, so this is minus k square rho square. Okay. Now here it is a function of only rho. This is also a function of only rho. This also depends only on rho. This depends only on phi. So I take this towards the right hand side and I bring this towards the left hand side. Okay. So what implies we get rho square by r d2 r by d rho square d2 r by d rho square plus rho by r dr by d rho plus k square rho square. This is equal to minus 1 by phi d2 phi by d phi square. Okay, this we call equation number 6. Okay, this is fine. Here again, the left hand side is a function of only rho, while the right hand side is a function of only phi. So here again, the left hand side is a function of only rho, while, let me write it on a new sheet of paper. While the right hand side is a function of only phi. Therefore, each side must be equal to the same constant. And let us say the constant is m square. See, there is what do we get? There is this minus 1 by phi minus 1 by phi d2 phi by d small phi square. Okay, this is equal to m square. This implies d2 phi by d phi square plus m square phi. This is equal to 0. Okay, let us call it equation number 7. And we also have to equate this left hand side to n square. So and we should write and and the other part is rho square by r. This is the left hand side, d2r by d rho square plus rho by r dr by d rho plus k square rho square. This is equal to m square. Okay, we multiply throughout by capital R and bring this m towards the left. Okay, so we get rho square d2r by d rho square plus rho dr by d rho plus k square rho square minus m square. We have multiplied throughout by r. This is equal to 0. This we call equation number 8. So we have obtained 3 equations. Okay, so we started with the Laplace equation, which is a partial differential equation, and now we have obtained 3 ordinary differential equations. Okay, what is the first equation? The first equation is equation number 4. d2z by dz square minus k square z equal to 0. And what is the solution of this equation? The solution is very simply z equal to c1 e to the power kz plus c2 e to the power minus kz. Simple solution. So let us first write the solution of equation number 4. The solution of equation 4 is given by capital Z is equal to c1 e to the power kz plus c2 e to the power minus kz. Okay, so let us call this equation number 9. So we have solved the first differential equation. And what is the second differential equation? So the second differential equation, ordinary differential equation, is this: d2 phi by d phi square plus m square phi. This solution is also simple. The solution is capital phi equal to c3 cos m phi plus c4 sin m phi. Okay, so let us write down the solution. The solution of equation 7. So the solution of equation 7. The solution of equation 7 is given by capital phi is equal to c3 cos m phi plus c4 sin m phi. Okay, c3 cos m phi plus c4 sin m phi. Let us call it equation number 10. Okay. Next, what is the third equation? Third ordinary differential equation. The third ordinary differential equation is this equation. Okay. This is the third ordinary differential equation. To solve this, let us substitute k rho as x. To solve this, let us substitute k rho as x, and this will become our Bessel equation. Okay, so let me write it here. In order to solve equation 8, let us substitute In order to solve equation 8, let us substitute this k times rho as x. Let us substitute k times rho as x. Okay. We can call it equation number 11. So if you put k times rho equal to x in equation number 8, I repeat, if you put k times rho equal to x in equation number 8, what does it become? So we multiply by k square here, k square here, so this becomes x square d2r by dx square. We multiply by k here, we get x dr by dx. Here this becomes x square minus m square r. Okay. So in order to solve equation 8, let us substitute this. Then equation 8, then equation 8 takes the form x square d2r by dx square plus x dr by dx plus x square minus m square capital R equal to 0. This is the Bessel. This is the Bessel differential equation. Bessel differential equation. Okay, this is the Bessel differential equation, and let us call this equation number 12. Let us write the answer on a new page. Okay, so this is the Bessel differential equation. So this is the Bessel differential equation, and its solution is given by its solution is given by R equal to C5 J M subscript M X plus C6 J minus M X. And if we put X equal to KR here, we get C5 JM KR plus C6 J minus M KR. Okay, this is for M as a fraction, where for M,
Sir,
yes,
KR or K rho.
sorry, KR, K rho. This should be K rho. K rho, sorry. Thank you. This should be K rho. Like for M as a fraction. So when M is a fraction, we get the solution as Bessel's functions of the first kind. Okay, and in general, this cell contain Bessel functions of the first kind and second kind. So or R is equal to C5 Bessel function of the first kind times K rho plus C6 Bessel function of the second kind Ym K rho. Okay, this we call 13A. This we call 13B. This is for M an integer. This is for M integer or in general. So we have obtained the solution for R, phi, and Z. Now let us combine these three solutions, okay, to obtain U. Thus, the general solution, of Laplace equation in cylindrical coordinates. In cylindrical coordinates, rho, phi, z is given by this u. It is a function of rho, phi, and z, and this is equal to r, which is a function of rho, multiplied by phi, which is a function of the angle small phi, and capital Z, which is a function of small z, and this is equal to for rho, for z, for phi. So first let us write the expression for z, and that was C1 e to the power kz plus C2 e to the power minus kz. Then let us write the expression for phi. Well, C3 cos m phi plus C4 sin m phi. Then let us write the expression for R, the general one. So C5 Jm k rho plus C6 Ym k rho. This we call equation number 14. And these solutions of Laplace equation in cylindrical coordinates are called general cylindrical harmonics. Okay, so this is the most general solution of Laplace equation in cylindrical coordinates. Okay, let me stop the recording here.